Hello students, welcome to the lecture number 12 on sequences and series. The learning outcomes for this lecture is we will learn the definition of an infinite series, the sequences of partial sums of an infinite series, and also we will discuss about the convergence of an infinite series. So first of all, what is an infinite series? Definition of an infinite series. Infinite series. Let an be a sequence. Then, if you insert plus sign between the terms of the sequence, then a1 plus a2 plus a3 plus so on up to infinity, denoted by this symbol, summation of n varies from 1 to infinity, is called an infinite series. So this is an infinite series. Next we learn about the definition of the sequence of partial sums of an infinite series. The sequence of partial sums of an infinite series. So let summation n varies from 1 to infinity. This is a1 plus a2 plus a3 plus a4 a5 and so on, be an infinite series. Now we make a sequence. We make a sequence Sn as follows. Let S1 be the first term of the series, S2 be the sum of first two terms of the series. Okay, S2 is the sum of first two terms, and S3 is the sum of first three terms of this series. Okay, sum of first three terms. Similarly, S4 is the sum of first four terms of the series, and similarly Sn is the sum of first n terms. Sum of first n terms of the series, and so on. So we have got a sequence whose first term is S1, second term is S2, third term is S3, fourth term is S4, and nth term is Sn. So we have got a sequence. This sequence is called the sequence of partial sums. The sequence of partial sums of the series of this series. Summation n varies from 1 to infinity. This sequence is called the sequence of partial sums. So this was the definition of the sequence of partial sums of an infinite series. All right. Next, we discuss about the convergence and divergence of a series. Convergence of an infinite series. When do we say that an infinite series is convergent? Right. So let summation n varies from 1 to infinity be an infinite series. All right. Uh, we say that the series, uh, right, let Sn be the sequence of partial sums of the series. Let Sn be the sequence of partial sums of the series. What does it that means? That means we have got a sequence whose first term is a1, second term is a1 plus a2, third term is a1 plus a2 plus a3, and similarly nth term is a1 plus a2 plus a3 plus an. All right, so you got a sequence whose first term and nth term is like this. So let Sn be the sequence of partial sums of this series. Then the behavior, then the behavior of the sequence of partial sums is said to be the behavior of this series. Okay, the behavior of the sequence of partial sums is called the behavior of the series. That is uh, the series an varies from 1 to infinity is said to be convergent. Convergent if what happens? If the sequence of partial sums is convergent, right? And if the sequence of partial sums converges to a number s, then we say that the series converges to the number s, converges to the number s, uh, or we also write uh, s is equal to the sum of the series. All right, s is equal to the sum of the series does not mean that if you add all terms of an infinite series then you will get s. It is all right. It does not mean that if you add all terms of a series then you get s. The sum of a series is s, means the series converges to s, and a series is said to converge to s if its sequence of partial sums converges to s. All right. Uh, the series is said to be divergent. The series is said to be said to be divergent to plus infinity or minus infinity if the sequence of partial sums diverges to plus infinity or minus infinity. All right, and we say that the series oscillates. All right, the series is said to be oscillating the series is said to be oscillating if the sequence of partial sums oscillates. So the behavior of the sequence of partial sums is called the behavior of of the series. So I hope this is clear to you about the convergence of a series. The behavior of the sequence of partial sums is, and how is the sequence of partial sums created? The sequence of partial sums is created like this. First term is a1. The second term is the first sum of first two terms of the series. S3 is the sum of first three terms of the series, and Sn is the sum of first n terms of the series. So this way you get a sequence, and that sequence is called the sequence of partial sums. The behavior of the sequence of partial sums is called the behavior of the series. And notice that when we write S is equal to sum of an as n tends n varies from 1 to infinity, which actually means that the series an converges to S, and the series an converges to S means the sequence of partial sums converges to S. So I hope all these definitions are clear to you. Now we move on to another important result. So we have a small theorem here which says the convergence, divergence, or oscillating behavior of a series remains unchanged remains unchanged by the addition or alteration of first finite terms of the series, of the first finitely many terms of the series. So we will show this. So here is the proof. So let summation n varies from 1 to infinity, and summation bn n varies from 1 to infinity be given series. All right, let summation an be a given series. All right, and let the series bn be obtained from the series an be the series obtained after deleting first m terms of the given series. All right, then What is the first term of the series B1? It is am plus 1, first m terms. And what is the second term of this of the series Bn is am plus 2, and similarly Bn would be equal to am plus n. So let summation let Sn and Sn dash be the sequences of partial sums of the series An and the series Bn respectively. Alright, then Sn dash is B1 plus B2 plus B3 plus Bn. This is the sum of first n terms of the series Bn, and this would be equal to Am plus 1 plus Am plus 2 plus Am plus n, and this can be written as A1 plus A2 plus A3 plus Am plus n minus A1 plus A2 plus A3 plus Am, and this is equal to the sum of first m plus n terms of the first series minus the sum of first m terms of the first series. So this implies the limit of Sn dash as n tends to of Sn dash as n tends to infinity is equal to the limit of Sm plus n as n tends to infinity minus limit as n tends to infinity of Sm. But this limit is same because Sm is a constant. As n tends to infinity, Sm would remain Sm. All right. Since n is finite, so this limit is finite, and uh, hence these limits, hence the sequence Sn and the sequence Sn dash converge or diverge together. Converge or diverge together. That means if limit of Sn exists, and limit of Sn dash also exists. All right, uh, and that means the series An and the series Bn have the same behavior, have the same behavior, because the behavior of the series is the behavior of their sequence of partial sums, and these two sequence of partial sums behave similarly because of this result. So we have proved that if you if you add a few terms to a series or alter a first few terms of a series, okay, if you add first few terms to a series or delete first few terms of a series or alter first few terms of a series, all right, then the behavior of the series remains same. Okay, the behavior of if it converges, it remains converging. If it diverges, it remains diverging. If it is oscillating, it remains oscillating. All right, the behavior of the series does not change by addition or alteration of first finitely many terms of the series. So this was uh, this result, and now we have another simple and important result. We have this theorem which says that if the series An converges to A and the series Bn converges to B, all right, then number one, the series An plus Bn this series converges to A plus B, and number 2, the series PAN or KAN, alright, the series KAN, n varies from 1 to infinity, converges to KA, where K is any real number, okay, where K is any real number. So if the series AN converges to A and series BN converges to B, then the series AN plus BN converges to A plus B, and the series K into AN converges to K into A. So let's do the proof. The proof is pretty easy. Let Sn 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 dash and Sn double dash be the sequence of partial sums, the sequences of the partial sums of the series AN, BN, and the series AN plus BN. Suppose these are the sequence of partial sums, then respectively, then Sn double dash is equal to A1 plus B1 plus A2 plus B2 plus AN plus BN, and this can be written as A1 plus A2 plus AN plus B1 plus B2 plus Bn, and this is equal to Sn plus Sn dash, and hence this implies the limit of Sn double dash is equal to the limit of Sn plus the limit of Sn dash. Alright, and the limit of Sn is A because the series AN converges to A. The series AN converges to A means the sequence Sn converges to A, and the series Bn converges to B means the sequence of partial sums of the series Bn converges to B. So Sn converges to A and Sn dash converges to B, and that implies the sequence of partial sums of the third series of the sum series converges to A plus B, and that proves the result, right? This implies the series AN plus BN converges to A plus B. So we have proved the first part. What about the second part? Uh, let Sn and Sn dash be the sequences of partial sums of the series AN and the series K times AN, okay, respectively. Then Sn dash is equal to Ka1 plus Ka2 plus Kan, which is equal to K times A1 plus A2 plus An, and which is equal to K times Sn. This implies the limit of Sn dash is equal to K times the limit of Sn, and the limit of Sn is A. This implies the limit of Sn dash is equal to Ka. Alright. Uh, why? Because the sequence, the series an converges to a implies that the sequence of partial sums of a converges to a. So this implies that the series k times an converges to k times a. So we have shown that if an converges to a, then the series k times an converges to to k times a. So this is all pretty easy, and let's do uh, one or two exercises based on the convergence of sequences. First of all, we have this exercise. Show that this series 1 plus 1 by 4 plus 1 by 4 square plus 1 by 4 cube and so on, all right, is convergent. All right, we have to show this. So to show a series is convergent, we have to show that its sequence of partial sums is convergent. Now Sn would be equal to the sum of first n terms of this series. The sum of first n terms of this series would be this, all right, and this is equal to the first term into 1 minus the common ratio raised to the power n divided by 1 minus 1 by 4, and this is equal to uh, 4 by 3 into 1 minus 1 over 4 raised to the power n. All right, so the limit of this implies the limit of Sn as n tends to infinity is equal to the limit of 4 by 3 into 1 minus 4 raised to the power n as n tends to infinity. So as n tends to infinity, this is just 4 by 3. All right. Hence, the sequence of partial sums of this series converges to 4 by 3. This implies the series, the given series converges to 4 by 3, or we also write that 4 by 3 is the sum of this series 1 plus 1 by 4 plus 1 by 4 square plus 1 by 4 cube plus so on up to infinity. We say that the sum of this series is 4 by 3. Alright, so this was one example. Now we have another example. Let's do another example. Another exercise is that show that this series 2 plus 5 plus 8 plus 11 plus 14 plus so on, this series is divergent. You have to show this series is divergent. So a series is divergent if its sequence of partial sums is divergent. Now the sequence of its the sum of first n terms of this series is uh, n into the sum of first n terms is n by 2 into 3n plus 1. This you can calculate. This is Sn is this is an AP 2 plus 5 plus 8 plus, all right, the nth term you can find out, first term plus n minus 1 into d is 3. All right, this is the nth term. So this is pretty easy that Sn is equal to this n by 2 into 3n plus 1. You can very easily calculate Sn, and if you take the limit of Sn as n tends to infinity, this comes out to be the limit of n by 2 into 3n plus 1 as n tends to infinity, this limit would be infinity. So this implies the sequence of partial sums is divergent. Divergent, and that means the series is divergent. That means the series, because the behavior of the sequence of partial sums is the behavior of the series. So the series is divergent. Alright. So let's this was exercise 2. Let's do another exercise, exercise 3. Show that this series minus 1 minus 1 minus 1 minus 1 minus 1 and so on diverges to minus infinity. Right. So a series is the behavior of a series is the behavior of its sequence of partial sums. So now Sn, the sum of first n terms of this series is minus 1 minus 1 minus 1. How many times? N times. So this is equal to minus n, and this implies the limit of Sn as n tends to infinity is the limit of minus n as n tends to infinity, and that is minus infinity. This implies the sequence of partial sums diverges to minus infinity, and that means the series diverges to minus infinity. All right, so these were some examples where we were discussing uh, the convergence of a series. Let's do one more important exercise. Consider show that the series 1 minus 1 plus 1 minus 1 plus 1 minus 1 plus 1 minus 1 and so on. This series oscillates finitely. Now if you write the sum of first n terms of the series, the sum of first n terms of the series would be 0 if n is even. Because if you take the 2 terms or 4 terms or 6 terms or 8 terms, the sum would be 0, and the sum of these terms would be 1 if n is odd. All right. So this implies the sequence Sn is the sequence 0 1 0 1 0 1. All right. This oscillates. So this implies the sequence Sn. All right. The terms of the sequence Sn are 1 0 1 0 1 0 1 0. That means Sn is an oscillating sequence. Is an oscillating sequence. So the sequence of partial sums is oscillating, so that we say that the series is oscillating. So the series is also oscillating. Um, so this way, similarly, we have this exercise which tells us to uh, show that this series minus 1 raised to the power n into n, all right, oscillates finitely, oscillates infinitely. So we show that this series oscillates infinitely by showing that the sequence of partial sums of this series oscillates infinitely. This is pretty easy to see. You can check it yourself. So we will end this lecture here. You can continue doing exercises which will be given in the adjoining in the adjoining video lecture. Thank you.